Welcome to lecture 25, where we start to talk about energy. We talk about types of energy, what is that concept all about. And we'll look at some examples of energy conservation, specifically transformation, and explain what we mean by that. Now, at the face of it, energy is in a sense like momentum, in that it is a quantity that is conserved, and we can use that to our advantage in calculation. But it is much more general than momentum. Momentum specifically was about the motion of an object, and mass times velocity, including the direction that is conserved overall, the total momentum. Now we'll have the total energy being conserved, but there are many more different forms that energy can have, so it works somewhat differently. Let's start by thinking about what types of energy there are. And so just think, what type of energy have you come across? Somebody's talking about this energy or that energy. Maybe pause the video and just see what you can come up with. Don't worry about being right or wrong or anything. Don't anticipate. Just what types of energy can you come up with? Chances are what you come up with is a relevant type of energy. But here's my list. Some of you might have heard of, some of you might not have heard of, some of you might have heard of by a different name. So one of them is kinetic energy. Kinetic energy is energy associated with motion of things. And I might have something big, sort of moving slowly. Might have something small that's moving fast. Might have something small that's moving very slowly, with less energy than something moving fast. Big thing maybe has more energy, but it would be even bigger, moving faster. That's just the motion associated with moving mass. Kinetic energy. Gravitational potential energy, roughly speaking, energy associated with being somewhere high up. It takes energy to climb up a hill. And then you're up there, well, you could climb on a cart and ride down and go fast. You just kind of have the potential up there to develop, kinetic energy. It's kind of why we call it potential energy. I'll talk about it more. Elastic potential energy. I squish a spring. Or maybe I have some kind of slingshot and I stretch a rubber band. Thermal energy, energy associated with things being hot. Definitely a type of energy. Chemical potential energy, essentially the energy associated with the chemical configuration of the molecules. Maybe we also have the atomic energy, the energy of an atom being in some particular state, whatever that means. Nuclear energy. The nuclear power stations. Well, that's energy associated with I guess, the nucleus of an atom in some way or another. Electrical energy. In many of those cases I wrote potential here. It'll make sense to you in just a second. Radiation energy. Energy associated with radiation. Say, solar energy, right? You might have come across. Well, energy from the sun, light, type of radiation. And I could probably list a couple more. So all of these quantities, they are, if you came up with any of them, great. You have some kind of intuition of some kind of understanding of what we mean when we talk about the notion of energy. But what then is it? When you hear people talk about energy, it's usually about converting one form of energy into another. For example, you might have the sun. The sun radiate with energy in its sunlight and the radiation, and by some method we turn into electrical energy with our solar power station. Or maybe we have fuel, right? Gasoline, chemical energy is stored in the fuel due to its molecular composition, and we can burn it. By burning it, well, we create thermal energy, but making it hot, but also that gets converted to kinetic energy. Our car is starting to move. So a lot of processes involve sort of changing between those. And that makes sense because the total energy overall is a conserved quantity. So what that means, we'll have processes where I start off with one kind of energy and I end up with another kind of energy, and the total before and after, the total amount of energy, is the same. And that can be useful in calculations. So let's write down what energy is. Energy is, what is it? Well, it's, with each of those we can associate a quantity. The quantity associated with what? What are we really associating this quantity with? So, for some of them I wrote potential. And potential is really, it's about the state or the status, the configuration of a system. Right? So something might have gravitational potential energy because it's high up on some hill. Right? Here's a little hill. There's an object up there. There's a lot of potential energy. That is the energy associated with the position where the object is high up. Or elastic potential energy. Imagine we have a spring, and the spring is squished. And I put a little ball here. You can imagine as I squish it, I shoot the ball over there. Right? Elastic band. I could take an elastic band. Maybe one of those sort of Y-shaped slingshots. I have an elastic band. I attach it. I stretch it. Put a ball in here, and I shoot it. In both cases, there's energy stored in the configuration, in the stretched band, in the squished spring. Now with chemical potential energy, it's with the structure of the particular molecule. And of course I can't redraw this accurately. You could imagine I've got some kind of molecule made of different atoms. They're hooked together by, physics that we haven't covered, that you might cover in a future course in physics or chemistry. But there's an energy associated with this, say, these atoms being in this particular molecular state compared to being in some other molecular state where they're differently arranged, or some of those bonds are broken or new bonds are formed. And so again, just with the kind of configuration that a system is in, there's a quantity associated with that. And then the nucleus of atoms can be in different configurations. Electrical potential, you can have essentially electrically charged particles that are in different configurations, and if you have that in a wire, then they create a current. But all of those essentially are kind of the same idea. Something about what state a system is in. There's a quantity associated with the state, the configuration, maybe the position of a system. This is for the case of potential energies. Or it's the state of its motion. And that would be kinetic energies, right? So kinetic energy itself is how quickly is mass moving. How much mass is moving, how quickly, that will determine the kinetic energy. Thermal energy is actually a type of kinetic energy. It is the kinetic energy of the individual little atoms that make up something. So when something is hot, like you boil your soup, there's a pot of soup, right? And there's soup inside, and it's hot, it's steaming. Well, that's because the atoms and molecules that make up the soup, they're moving very fast. Whereas when they're cold, soup has been in the fridge, well, then they don't move as fast. So it's kinetic energy of individual atoms added up. That's what thermal energy is, and you might cover that in more detail in a future course. Radiation is a little bit more complicated to explain. It's essentially the motion of fields. It's electric fields, magnetic fields, in the case of light, those two together. But you could also imagine other types of radiation. Again, this is something we're not going to go into here, because there's other physics we'd want to cover first, and we might again do that in a future course. But the idea is always the same. There's some kind of quantity you can associate with the state or the motion of a system, and then the total is conserved in any process. Let's write that down. Let me write it down here. Total energy is conserved in any process. Now, in many processes, some types of energies that are listed up there are irrelevant, right? For example, let's take this this car. Imagine there's a car or a ball on a hill, and I push it down, it starts rolling, it speeds up. Well, gravitational energy is turned to kinetic energy. Maybe there's friction, which is going to make things warm up a bit, like if somebody pushes the brake, it'd be thermal energy. But there's no nuclear transformation, no radiation, no chemical changes. So those other types of energies might not be relevant, and I can ignore them in my analysis of the situation. But what's conserved is the total of all of those. It's just I don't have to worry about the ones that don't change in the first place in the particular situation, in the particular process that I'm looking at. And if that sounds a bit abstract, a bit confusing, don't worry, we'll see some examples that will clarify it a lot. What I'm going to do right now, though, is look at some examples of energy transformation. This is my first example. This is a terribly drawn archer. Even for my stick figure drawings, this is a bad one, but let's go with it. This is an archer shooting a rather large arrow. So what's the arrow going to do? It's going to start moving. It's going to fly through the air here, and then over here, maybe it'll hit a tree. Draw a little tree here, where the arrow is eventually going to get stuck. Right. So what types of energies are converted to what other types of energies? So energy conversion, energy transformation means I maintain the same total energy, but it's moving, the quantity is moving from one type of energy to another type of energy. So in this case, the archer is starting out with elastic potential energy in the bow. Right, the bow is stretched, pulled back. There's energy stored in having this tension in the bow. Elastic potential energy. Then the archer lets go. So now the arrow gains kinetic energy. Right, of the arrow. Maybe we should write this. This is of the bow. This is in the arrow. Then maybe the arrow actually goes up in the sky. It might slow down as it goes up and might gain some gravitational potential energy. So graph, and I want to use PE for potential energy, and it still has some kinetic. It doesn't ever quite stop, even if it goes up. It's still going sideways, for example, even at the highest point. It might come back down, in which case it speeds up again, so I'm going to go all to kinetic energy, KE, kinetic energy. Then it'll get stuck in the tree, and at that point the kinetic energy is, well, it disappears, but you can hear it. There's energy associated with the sound. In a way, it's a kind of radiation energy. This energy associated with wave motion. I'm going to write sound energy. Don't have to be technical right here. Sound energy, and actually it might also get a little bit warm. This will be hardly measurable, but you might get some thermal energy right where the arrow gets stuck. Maybe if you had like a gun and you shot a bullet at some kind of object, you could feel that it's going to be warm around where the bullet hit if the bullet gets stuck inside, for example. And the sound energy eventually will dissipate, and it'll also actually turn into a little bit more thermal energy. Why? I don't want to go into that right now. Right? But often thermal energy is kind of the end result of some process that you might come across in day-to-day life. So this is an example of energy transformation. So I could go further back, of course. Where did elastic potential energy come from? Well, the archer was using their muscle, right? Their arm muscles to pull back the bow. So there was some kind of conversion of metabolic, that's really a type of chemical potential. Where did the archer get that energy? Probably from breakfast. So breakfast energy. Of course, it's also just another type of chemical energy. I'm gonna write breakfast. Where did the breakfast come from? Oh, probably maybe the archer had some oats and those grew in a field, right? Where did they get their energy from? Those oats that were growing there. Probably part of it from the sun, part of it from other chemical energy. So you can kind of trace this on. I could also see what happens to the thermal energy. Right? It's hard to keep it as an isolated system there, but you can always trace this line of energy conversions further forward, further back. And probably, for the purpose of a mechanics course, I'd probably be interested in this part here. But those are the types of energy we'll be seeing more of. There's chemical energy and so on. Well, we'll leave that to other courses. Let's do another example. In this example, I imagine I have a car that goes up a hill. Well, the car's right here, it's going up a hill. So how does it do that? Well, it might have some initial velocity when it gets there. But that might not be enough to have it go up the hill, right? But it has an engine as well, and that engine keeps burning fuel, making the car go up. So what do we have? Well, let's start with the fuel, right? The fuel would be chemical energy that gets burned, and the burning creates some thermal energy because it's hot and heats up the engine, heats up the surrounding a bit. Bit of a waste, right? It's not really useful to us, but also we get kinetic energy. That's the type we want. Sadly, we can't get 100% efficiency where all the chemical energy gets turned to kinetic energy. There are very profound limitations to thermodynamics that make that impossible. Then it goes up the hill, and the kinetic energy, as well as more chemical energy, gets turned to gravitational potential. As a continuous process, I keep burning fuel, and maybe if I go up at a constant speed, I really could sort of have an arrow from here directly to there as well. And then the car ends up the hill. If it rolls back down, maybe we can imagine the car turns off its engine. So turn off engine and enjoy the ride down, just using gravity. Well, then this would get turned again to kinetic energy. If the car hits a tree, we get more sound energy, more thermal energy. Probably not very useful in a sense, right? And where's the chemical energy come from? Well, from the gasoline, which what's that? I guess they're dinosaurs. They had food. You know, again, I can go backwards a really, really long time. And yes, I know it's not just the dinosaurs that make up crude oil. But just another example of energy transformation from one stage to another. And always the total energy is conserved. So in every case, I can associate a numerical quantity with each type of energy. And the total of those quantities, the sum, is conserved. But very often I'm unable to actually track the exact values. So some of those processes I can sort of describe in words, but I can't actually use for a calculation. But there are other cases where I can use this conservation of energy for calculations, and some of those are the ones we'll be looking at in this course. Let's do one more example. An example I'm envisioning now is the sun. Let's just call it that, the sun. So here's the sun. What's happening inside? Inside there is fusion, and these are nuclear processes. There is nuclear energy, and that is released. You might say, well, what does that mean? That means that nuclear energy becomes thermal energy to a great extent. It also causes radiation. So we're going to have radiation. The energy in the light and other electromagnetic waves that get emitted by the sun. Maybe that radiation hits some kind of solar panel. Here's a solar panel. Maybe you have some satellite. Right, so this is a solar panel. The radiation is converted into electrical energy. Maybe the electrical energy charges a battery, right? And the battery would be potential energy, or maybe it powers some kind of engine. Whatever happens next, so there's again this process of gradual conversion. Now, in this class, most of those we're not going to deal with, they're complicated, they're often hard to track, they're not useful for mechanics. Right? If there's a process where the sun, through fusion, creates radiation, that is something we can't track with the tools we develop in this course. That's the subject of a future physics course you might take. Energy will be, you'll see energy in pretty much any course you might take after this one. I guarantee it. So what types of energy are we going to be looking at? Types of energy in this course. What types are we actually going to do calculations with? Well, kinetic energy is important. And we're looking at gravitational potential energy, and we're graph pot energy. We'll be looking at elastic energy, say in a spring, in a stretched or squished spring, or in a rubber band. And maybe other types of potential energies. Maybe even some sort of general potential energy where we don't know exactly what type it is, but we can still work with it as examples. And you'll see what I mean when we get there. Each one of those has an expression. I mean, here I don't know, right? Depends on the type. But for this one, for example, I might write what's 1/2 times the mass times the speed squared. Why is it that? We'll talk about it, but not right now, right? Point is, there's some mathematical expression, depending on the mass of the thing that's moving, its speed, and that'll determine the energy. Gravitational potential energy, we're going to meet one first. It's mass times g times height. G is the acceleration due to gravity, or I could write it as weight times height. We're going to meet a second expression, more general expression for gravitational potential energy later in the course when we talk about Newton's theory of gravity. But again, the main point is there is some mathematical expression. Elastic potential energy, let me write 1/2 times the spring hardness, because that's defined in more detail, but let's just call it how hard is your spring. Some value can associate with that, times the stretch distance, could be a compression too, squared. Why? Never mind that right now. We'll talk about why. We'll figure that out. Where do these expressions come from? The point right now is there is one expression for each type, and later on, when some process happens where kinetic energy is turned to gravitational potential or elastic to kinetic energy, or whatever it is, the total sum of these, that is what's going to be conserved. Again, it's a bit of an abstract lecture and a very sort of broad overview over what the concept of energy is. If it still seems a bit mysterious, that's okay. We're going to talk about it in detail. We're going to be looking at examples, and hopefully that all makes sense then. Right now, what I'm going to say is that all these types of energies, I could call them all mechanical energy. And broadly speaking, is the energy associated with the kind of macroscopic properties, the large properties of the system, the things you can see. You can see how high up it is, how fast it is moving, and how stretched a rubber band is. We're not going to worry about those sort of invisible ones, like the molecular structure, the ones you can't sort of see by just looking at it, or the nuclear potential energy. Again, something you can't really see, you can measure indirectly. We're going to be worried about the ones where I can look at the object. Where is it? Okay, how high up is it? How stretched is the spring? The stuff you can access very easily. So I'll see you in the next lecture where we'll start applying some of these ideas in some detail.